Okay, we are on to page 18 of the packet, so 2 more pages to go. We got a little solving equations, and they're actually not equations, they are inequalities. So solving inequalities, my recommendation for this is to just treat as an equation, meaning replace with an equal sign, and then deal with it later. So I really want to know where is the interesting or important points, and then we can figure out different ways of knowing, well, are we actually greater, less than, equal, so on. So first of all, I'm going to add 5 to both sides to this equation. So we'll get 3 to the power of x minus 4 is equal to 3. I could use logs here, but I won't because this is 3 to the first. So I'm just going to say if 3 to the x minus 4 equals 3 to the first, well then x minus 4 has to equal 1, x has to equal 5. Great, but now we need to think about our inequality. So method number 1 here is imagine the graph. 3 to the x minus 4, that's an exponential curve. And it's down 5 relative to the x-axis. And I'm just taking some other guesses about where it might be. But maybe it looks a little something like that. And we said x equal 5 is the cutoff point where we're greater than -2. So maybe -2 is right around here. And that's our cutoff point, right? That's where x equals 5. And so if I want to be greater than that, well, all of this to the right of that point is going to be greater. So my answer is just going to be x is greater than 5. A second method I could use is I could draw a little number line. I've got this important point 5 on the number line, so I can test above and below and see what's actually true. So for example, if I test a point below 5, I could do 3 to the 4 minus 4. So I'm testing 4 minus 5 greater than -2. And so then 3 to the 0 minus 5 is greater than -2. That would be 1 minus 5. So I would get -4 is greater than -2, which is false. So this area is false. And that right here corresponds to all of this, right? That's a point in that zone. Then I can test an area to the right if I want to be safe. So I could do like 3 to the 6, right? I test 4 over here, maybe I test 6 over here. -4 minus 5 greater than -2. That would be 3 squared minus 5 greater than -2. 4 is greater than -2. That's true. So this is true. And that means that this is probably, or not probably, this is my solution, right? That's what corresponds over here. So you can test points, or you can sort of visualize it, or mix and match as you see fit. Okay, we have a rational inequality now. So again, I'm going to treat it as an equal sign. Just going to multiply both sides by x plus 3, giving me 6 equals x plus 3. Subtract 3 from both sides, and I get x is equal to 3. Okay, so I want to know, well, is that greater than 3, less than 3, and which is it? If I think about my function on a graph, 6 over x plus 3, the thing to note is, one, there's a vertical asymptote at x equal -3, okay? X equal -3, we have a vertical asymptote. Then I'm interested in when is the function greater than 1. So that's not actually part of the function, but that's what I want to know. When are we greater than 1? I also know that I have a horizontal asymptote at y equals 0, and x equal 3 is where I intersect with this line. So somewhere over here would be like x equal 3 is where I intersect with this line. So knowing all these facts about the function, like we probably go something like this. And then on this side, maybe we look, actually, I don't know. That's a little interesting. Something like, maybe we're down here. Because, right, that's not a horizontal asymptote. That's just a random line, y equal 1. So we don't cross the x-axis. Anywho, so I want to know when are we greater than that? And that happens to be when we are in here. Okay, that's when we are actually greater than this line. Based on that information, I can say for x greater than -3, because -3 is undefined, or less than equal to 3. So that's going to be my answer. One thing to note is with these rational functions, like on that vertical asymptote, that breaks our function up. So if I go and do my line test, perhaps we like that method for this one instead. I found 3 that I want to test, but I also have that vertical asymptote at -3. So it's really important to test 3 regions because there's this intersection place. So we want to know, are we greater than or less than there? But then the function also gets broken up by this vertical asymptote. So I sort of have 1, 2, 3 areas to be interested in. So let's plug in some points. Let me try 0. So if I do 6 over 0 plus 3, that's 6 over 3, aka 2, which is greater than or equal to 1. So that's true, meaning this region works. Test a point in here, so maybe 4. So 6 over 4 plus 3. That would be 6 over 7, and that's a fraction that's less than 1, right? Less than 1. So that would be false. So this region is false. Here I'm including 3 because it's greater than or equal to, but this is the vertical asymptote, so I'm not going to include it. And then I can just test my last region. So I could do 6 over, maybe I try -4. -4 plus 3, so that's 6 over -1 is -6, which is less than 1. So that region is also false. So we come to the same conclusion that x has to be between -3 and 3, but it can be 3. So you can either try to visualize the graph. For this case, it's actually pretty hard, or you can go and do the number line. Be really careful, though, that that vertical asymptote, that's got to go on the number line, because that breaks my function. So whatever was happening over here, like we were going woo, 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 up, like maybe we're over here, maybe we're not. So you've got to use that as a test point, which we can see in the next one. So looking at number 11, it says solve x plus 1 over x times x minus 5 less than or equal to 0. Right away, I mean, this is starting to get more and more complicated, right? This rational function, we want to know basically when is it negative or 0. So if I try to visualize this, x plus 1, so I have an x-intercept at -1, comma 0. If I plug in 0 for x, we're undefined. We have a vertical asymptote here at x equals 0. And we also have a vertical asymptote at x equals 5. Okay, so that's 5. So we're kind of chopped into a couple of regions here already. We have 1, 2, 3. 1, 2, 3 regions we might need to test. We also, the degree of the numerator is less than the denominator, so we're going to have a horizontal asymptote. Logically, we would have it at, y equals 0. Remembering that for rational functions, it's an end behavior asymptote, so we can go through it. It's just eventually we're going to level out there. And yeah, once we solve this, we're going to get even more information. So we want to know, when is this function? Is it down here? Is it down here? Is it down here? When is it less than or equal to 0? So we're going to have a lot of stuff to test, but let's go through the algebra and see what happens. So I'll get x plus 1 and replace it with an equal sign, multiply this by both sides, but 0 times anything is 0. So I get x equal -1. So that's giving me that x equals -1 is my only point that I'm actually having to work with in addition to those vertical asymptotes. Let's see. Is there anything else that we could use here? Not really. Like, even to graph this function, we would probably want to test points, because I don't really have a good way of knowing, like, are we here or are we here, right? Am I here or am I here? And then I don't know what's happening here. Like, maybe we go through and come back and have this end behavior. So like there's too much happening. We'd have to test points to graph this thing anyways. So let's take it over to the number line. So on our number line, we said we have this -1 is sort of our x-intercept. That's where we cross that line 0, which we're interested in. When are we less than 0? Then we got to check our vertical asymptotes, which are at 0 and +5. So I've actually got 4 regions to test, corresponding to 1 area, 2nd area, 3rd area, 4th area, because I don't know whether it's positive or negative in each of those little areas. So let's get plotting points. Let's start with 1. So we'll do 1 plus 1 over 1 times 1 minus 5. And I can really quickly see that that's going to be 2 over negative 4. So it's negative 1 over 2, which is less than or equal to 0. So that's true, okay? Meaning in this 0 to 5 region, my function has got to be down here somehow. And it doesn't cross that 0 line, so cool. In that whole region, it's true. So I'll put some open circles here because we can't be 0 or 5. Those are our vertical asymptotes. Then let's test if it's greater than 5. So I'll do 5, or let's do 6 plus 1. So we'll test 6 over 6 times 6 minus 5. I can tell that's positive, so that's 7 over 6, which is not less than 0. It's greater than 0, so that is false compared to this, which was true. So it's false here, which means that we got to be somewhere up here. Neat. And this is great practice in graphing rational functions too, which I think we're going to have to do on the next page. Now we can test, well, let's test these regions. So I can test here, I'll test negative 2. So negative 2 plus 1 over negative 2 times negative 2 minus 5. Numerator will be negative 1. Denominator is going to be negative times negative, positive 14. So that is less than or equal to 0. That is true. So this region is true, and we include that point. And now I can pretty much guarantee, so maybe we look like this. That's kind of weird. We approach it like that, that this region is going to be positive because I cross through this x-intercept of negative 1, 0, and I don't come back ever. So I know I'm shooting off to infinity, but just to prove it to you, I could do like negative 1/2 perhaps. So I could do negative 1/2 plus 1 over negative 1/2 times negative 1/2 minus 5. Which tells me the numerator is positive, 1/2. The denominator is a negative times a negative. Negative 1/2 minus 10/2 is negative 11/2 times negative 1/2 is positive 11/2. Positive over positive, 1/2 divided by 11/2 is 11, I'm pretty sure. No, is 1 over 11, which is greater than 0, which is false. Okay, so this is false. True. So all said and done, our answer is going to be x is less than or equal to negative 1, or x is between 0 and 5. Okay, and if we look at our graph, it sort of reflects that. You could graph it on Desmos or your calculator to confirm. So that's pretty tricky, but if you note your vertical asymptotes, you solve your equation, find that point where it's equal 0, and then that shows us 4 regions that we split into to test. You'll be in good shape. All right, cruising on, we're going to do a little polynomial division. A little throwback here, can be useful. So we're going to divide the polynomial x to the 4th minus 2x cubed plus 15x. I'm going to go ahead and do something here. I'm going to put plus 0x squared plus 15x minus 2. With polynomial division, it can be really helpful to have that placeholder so you don't forget. And I don't know, it's not 100% necessary, but it might save us. All right, so first thing you do, you just look at the lead term and the lead term. So how many times does x go into x to the 4th? Well, x cubed times. Then you multiply this back by x, so you get x to the 4th, multiply back by 2, so we get plus 2x cubed, and we subtract all of that. So this cancels, that's the whole point. Negative 2x cubed minus 2x cubed gives us negative 4x cubed, and then all this other stuff comes down. Yeah, I guess for educational purposes, I'll bring it down. You could just leave it up there and just know it's there, but it's a little sloppy. All right, how many times does x go into negative 4x cubed? Well, negative 4x squared. So that's where this placeholder sort of helps me put it on top of the x squareds. Multiply it back, negative 4x cubed. And then 2 times negative 4x squared is negative 8x squared. Again, that placeholder, kind of nice to have. Subtract, cancels. 0 minus negative 8x squared is positive 8x squared. Everything else comes down, so plus 15x minus 2. How many times does x go into 8x squared? Well, 8x times. Multiply it back, we get 8x squared, and then plus 16x, and then we are subtracting. Bummer, we're gonna have a remainder. Okay, so we go subtract this, and we get cancels, then we get negative x, minus 2 comes down. Or maybe no, we're not gonna get a remainder. Never mind, I lied. So how many times does x go into negative x? Negative 1 times. Then negative 1 times x gives me negative x. Negative 1 times positive 2 gives me negative 2. Subtract it, cancels, cancels. I get a remainder of 0. Wahoo! So our answer is x cubed minus 4x squared plus 8x minus 1. Very nice. All right, so that's a little bit of polynomial division, a little refresher for you. And we are on to the last page, last problem. It says, graph the following rational function, make all important features clear, state the points of discontinuity, state the domain. All right, couple of things to do. First of all, I want to look for the degree. So the numerator has degree 3, denominator has degree 3. So that means I'm going to have a horizontal asymptote based on the lead coefficients, which are 2 and 1. So at y equals 2 over 1 or 2. So I'll just throw that on my graph, put it down. Great. Looking for common factors in the numerator and denominator, I don't see any. In the numerator, we have x plus 2, x plus 2, I should keep that 2 there, x minus 5, compared to the denominator, which has x plus 5, x minus 2, x minus 2. Okay, so seeing as there's no common factors, each of these corresponds to a vertical asymptote. Doubling up on a vertical asymptote doesn't really do anything. So we'll have a vertical asymptote at x is equal to 2 and at x equals negative 5. 1, 2, 3, 4, 5. Okay, so my function has been nicely chopped into 3 regions. Let's keep looking for information. So based on the numerator, I can get my x-intercepts, right? Because if I set this whole thing equal to 0 all over my denominator, it doesn't really matter what the denominator is. Like, I can just multiply both sides by the denominator, and 0 times this is just going to give me still 0. So I'll get 2x plus 2 squared, x minus 5 equals 0. And then zero product property will tell me that x equals negative 2 and x equals 5. So those are my x-intercepts. So negative 2, 1, 2, and positive 5, 1, 2, 3, 4, 5. Okay, so that's starting to piece us together. Getting some information about our function. We could see about a y-intercept. So if I plug 0 into the function, so if I go to 2, 0 plus 2 squared, 0 minus 5, all over 0 plus 5, 0 minus 2 squared. This is going to give me 2 times 4 times negative 5 over 5 times 4. Cancels, cancels, but it's negative 1. So that's going to be 0, comma, negative 2. Seeing as that's the only place we cross this axis, I can safely say we're going to shoot on down somehow here, because I can't cross the x-axis again. And because we have x plus 2 squared, remembering back to polynomials, that multiplicity of 2 tells us we bounce off the x-axis at that point. So that still should apply here. So when I come up here, I'm going to bounce off. If I bounce off, that means I'm heading down on infinity. You could plug in points and test that, but yeah, that is what it is. Other thing we can do here, so I'm going to erase all this, is see, do we cross this horizontal asymptote ever? because that'll get us some important information. So if I set my whole function 2x plus 2 squared, x minus 5 equal to 2, and this is supposed to all be over x plus 5, x minus 2 squared. If I set it equal to my horizontal asymptote, I'll be able to know if it ever crosses. And if it doesn't, that's really going to bound me in. Like I could go like this if it doesn't, and then I'd also go like this, because if I were down here, that would mean I'd need another x-intercept, which I don't have. So let's solve that equation and find out, do we in fact cross it? Multiply both sides by my denominator, and I'm going to just divide everything by 2, cancel that. So I'm going to get x plus 2 squared, x minus 5 equals x plus 5, x minus 2 squared. Remember when I told you need to be able to square a binomial because it just comes in handy a lot? Guess what? Let's square our binomials. So x squared plus 4x plus 4 times x minus 5, x plus 5 times x squared minus 4x plus 4. Okay. Good. Now we use the distributive property. Everything distributes. You can set up a box method if you like, but I can distribute, 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 so on and so forth. So I get x cubed plus, well, let's do it this way. X cubed minus 5x squared plus 4x squared minus 20x plus 4x minus 20 equals distributing x cubed minus 4x squared plus 4x plus 5x squared minus 20x plus 20. So I could combine like terms as much as I like, but I'm going to cancel everything that's on both sides. So x cubed, gone. Let's look. Minus 20x is gone. 4x. I mean, when I say gone, it's because I can subtract x cubed from both sides, right? I can add 20x to both sides, and I can subtract 4x from both sides. So that leaves me with 4x squared minus 5x squared. So that's going to actually be negative x squared. These make negative x squared minus 20 equals, this side I'm going to end up with positive x squared plus 20. Yeah, so this is looking interesting because let's factor out negative 1 times x squared plus 20 equals x squared plus 20. Dividing both sides by x squared plus 20 gives me negative 1 equals positive 1. But that is false, right? So we set up this equation trying to see, do we cross the horizontal asymptote? And the answer is no. We can't come up with a solution of x that actually crosses this asymptote of 2. Okay, we don't cross the HA. Remembering that on a rational function, the HA horizontal asymptote's an end behavior asymptote, so eventually we've got to trend towards that. But in the meantime, like theoretically, I can go whoop, whoop. But in this case, we don't. So if we don't cross, well, guess what? If I need to go through this intercept, then that means my function's going to look a little something like this. And if I can't cross this axis, right, that's not allowed because I would have another x-intercept, well, I'm going to be up here. And that's a beautiful graph of our function. And if you head over to Desmos or TI-84 graphing calculator, you'll see that this looks pretty good. Points of discontinuity. So we don't really have points of discontinuity. Our discontinuities are vertical asymptotes at x equals negative 5 and x equals positive 2. What other important features? The domain is all real numbers except x does not equal negative 5 or 2. I don't know, we have all our x-intercepts on there, right? We have 5, 0. We have negative 2, 0. We have our y-intercept of, what did we say that was? 0, I guess I erased, but negative 2. So I think we're good to go. Awesome. Well, if you stuck with me for this packet, thank you. I really hope you found it useful. Very nice work. If If you have questions, please let me know. Nice job. All right. Thanks for watching. Like and subscribe.